Hello everyone! In this video, we're going to discuss and solve problems involving derivatives of logarithmic function, particularly the natural logarithm. But before we can do that, let us first discuss the formula for the derivative of natural logarithm. So, if we are given a function of u, alright, so if we are given u as a function of x, and the given function is y equals ln of u, then y prime would now be equal to the derivative of u with respect to x all over u. So this would now be the formula that we are going to use. Now, in solving problems involving derivatives of logarithmic functions, it is also important to recall the different properties of logarithm. So for some properties of logarithm, so if we're going to recall it here, some properties of logarithm, we have the logarithm of a plus the logarithm of b can be written as the logarithm of a multiplied by b. Alright, so where a and b are functions of a variable. Logarithm of a multiplied by logarithm of or minus logarithm of b, that is equal to the logarithm or the natural logarithm of a over b. And the natural logarithm of a raised to a constant can be written as k multiplied by the natural logarithm of a. So these are now some of the important properties that we can use when we're dealing with derivatives of logarithmic functions. Because if we're going to take advantage of these properties, then our solution might be easier than that of getting the derivative of product, of a quotient, and so on. Right? So to illustrate this further, let's have our first example. We are given y equals the natural logarithm of 7 minus 3x, and we're going to solve for y prime. Alright, so again, using our formula, the derivative with respect to x of natural logarithm of u, where u is a function of x, then this is now equal to the derivative of u with respect to x all over u. So applying this formula, the given function, alright, so this 7 minus 3x would be u, so y prime would now be equal to the derivative with respect to x of 7 minus 3x all over 7 minus 3x. Right? So solving for y prime, then this is now equal to the derivative of 7 is 0, the derivative of negative 3x is negative 3 all over 7 minus 3x. Now we can write this as negative 3 all over 7 minus 3x. And since the resulting expression cannot be simplified any further, then this is now the derivative of y. For the second example, we are given y equals the natural logarithm of sine 3x, and we're going to solve for y prime. Now, if we're going to inspect the given, the argument sine 3x would be u. And again, the derivative with respect to x of the natural logarithm of u is equal to du over dx all over u. And since the argument is a trigonometric function, then it is also important to recall that the derivative with respect to x of sine of u is equal to positive cosine u du over dx. Alright, so using these formulas to solve for y prime is now equal to the derivative with respect to x of cosine or sine of 3x, I should say, all over u, which is sine of 3x. Now, the derivative of sine 3x is equal to cosine of 3x multiplied by the derivative of u, and u in here is 3x, the derivative of 3x is equal to 3, all over sine 3x. So y prime is now equal to 3 multiplied by cosine of 3x all over sine 3x. Now, note that cosine of x over sine of x is equal to cotangent of x. So, cosine of 3x all over sine of 3x can also be written as cotangent of 3x. So this would now be our final answer. So let's have another example here. We are given y equals the natural logarithm of the natural logarithm of x, and we're going to solve for y prime. So again, in the given function, our argument natural logarithm of x in here would be our u. So since the form of the given is in natural logarithm, then y prime is now equal to the derivative of u, alright? So that would now be derivative with respect to x of u, which is the natural logarithm of x, all over u, which is ln of x, alright? And for the numerator here, this is now equal to the derivative with respect to x of u in here is x, so that would be x all over x. All over, alright, so all over the natural logarithm of x. So let me just bring this down. There we go. Alright, now the derivative of x with respect to x is equal to 1 over x all over ln of x. And simplifying the resulting expression, y prime is now equal to 1 over x multiplied by ln of x. So this would now be our final answer. Let's have the fourth example here. We are given y equals the cotangent of the natural logarithm of x, and we're going to solve for y prime. Right? So the formulas that we are going to use in here would be the derivative with respect to x of cotangent of u, where u is a function of x, and this is equal to negative cosecant squared of u du over dx. And since our argument in the given function is ln of x, this would be our u in here. Alright? So the formula for the derivative of natural logarithm of u is du over dx over x, or I should say u. Right? So if we're going to apply these formulas, we can now solve for y prime. So this is now equal to cotangent of u is negative cosecant of squared of u du over dx, so that would be negative cosecant squared of ln of x multiplied with the derivative with respect to x of ln of x. And the derivative of ln of u is du over dx, so this is derivative of x with respect to x is equal to 1 over u, so that would now be equal to x. Alright, so this is now equal to negative cosecant squared of ln of x multiplied by the derivative of u, so that's 1 over u, so that's x. Alright, so if we're going to rewrite the expression, so this is now equal to negative cosecant squared ln of x over x. This is now y prime. For example number 5, we have y equals x squared ln of x, and we're going to solve for y prime, right? If we're going to inspect the given function here, this is in the form of u times v, alright? So x squared is our u, and this is our v. So applying the formula, y prime is now equal to x squared multiplied with the derivative with respect to x of ln of x plus ln of x multiplied with the derivative with respect to x of x squared. So this is now equal to x squared multiplied by the derivative of ln of x, right? So that is 1 over x, or that's the derivative of x with respect to x over x, plus ln of x multiplied by the derivative of x squared, so that is 2x. Now, simplifying this, we have x, right? So x will cancel out with x in here, and plus ln of x, or that's 2x ln of x. Alright, so if we're going to factor out x in here, so that would now be x multiplied by 1 plus 2 ln of x. Or by properties of logarithm, we can also write this one as x1 plus ln of x squared. Alright, because k, or a constant, multiplied by the natural logarithm of x can be written as ln of x raised to the constant. So if this is 2 ln of x, then we can write it as ln of x squared. So this would now be our final answer. For our next example here, we are given y equals x ln of a squared plus x squared plus 2a arctangent of x over a minus 2x. So the requirement here is to solve for dy over dx. Now what we can do here is to solve for the derivatives of each term independently, applying all the formulas that we have discussed. Right? So for this one, this is in the form of u multiplied by v. This one is in the form of arctangent of u, where u is x over a, and this is the derivative of negative 2x is actually equal to negative 2. Alright? Now, since the requirement is dy over dx, then a will be considered as constant in here. So, solving for y prime, this is now equal to, right? So, this is u times v, so that would be u dv plus v du. So, that's now equal to x derivative with respect to x of the natural logarithm of a squared plus x squared plus the natural logarithm of a squared plus x squared multiplied by the derivative with respect to x of x, right? So this is the derivative of the first term. And for the derivative of the second term, so that would now be plus 2a multiplied, right? So if we're going to recall, the derivative with respect to x of arctangent of u is equal to du over dx all over 1 plus u squared. So that would now be derivative with respect to x of x over a all over 1 plus x over a quantity squared. And for the last term, the derivative of negative 2x is now equal to negative 2. So solving further, this is now equal to x multiplied by the derivative of ln of a squared plus x squared. Alright? The derivative of ln of a, or ln of u, where u is a function of x, is equal to du dx all over u. So applying that formula, we have the derivative with respect to x of a squared plus x squared all over a squared plus x squared plus ln of a squared plus x squared, derivative of x with respect to x is equal to 1, plus 2a multiplied by the derivative of x over a, so that is 1 over a, all over 1 plus x squared over a squared minus 2. Alright, so this is now equal to x multiplied by the derivative of a squared with respect to x, so a is considered as constant, so that would be equal to 0, plus the derivative of x squared, so that would be 2x, all over a squared plus x squared, plus the natural logarithm of a squared plus x squared. And for this term, alright, so a in here will cancel out with a in here. And for the denominator here, if we're going to simplify that one, that would now be a squared plus x squared. So if we're going to simplify this, alright, so if we're going to simplify this, then that would now be plus 2a squared all over a squared plus x squared. Because a multiplied by 1, then that is now the numerator of the result multiplied by 2, so that is 2a squared. And then we have a squared plus x squared, so that would now be our denominator, minus 2. Alright? So simplifying further, this is now equal to 2x squared all over a squared plus x squared plus the natural logarithm of a squared plus x squared plus 2a squared all over a squared plus x squared minus 2. Now, if we're going to combine these two terms here, this is now equal to 2x squared plus 2a squared all over a squared plus x squared plus the natural logarithm of a squared plus x squared minus 2. And if we're going to factor out 2 in the numerator here, then we have 2 multiplied by x squared plus a squared all over a squared plus x squared plus the natural logarithm of a squared plus x squared minus 2. Now, we can cancel out x squared plus a squared and a squared plus x squared in here, thus leaving us 2. So if 2 will now be the remainder here, minus 2, then this will also cancel out in here. Thus, y prime is now equal to the natural logarithm of a squared plus x squared. So this would now be our final answer. For our next example, we are given here y equals the natural logarithm of 1 plus x squared all over 1 minus x squared, and we're going to solve for y prime, right? So in here, if you're going to inspect the given function, right, so this would be our u, and u is in the form of u over v, or is in the form of a quotient. Now, if we can apply the properties of logarithm in order for us to make our solution easier, then we do so, right? So since the given function is in the form of the natural logarithm of a over b, and ln of a over b is equal to ln of a minus the natural logarithm of b, then we can write y b equal to ln of 1 plus x squared minus ln of 1 minus x squared. Now, in this way, it's easier to determine the derivative of the logarithm by determining the derivative of each term, right? Now, again, the formula for the derivative of natural logarithm is equal to the derivative of u with respect to x all over u. So applying this formula, we can now solve for y prime, which is now equal to the derivative with respect to x of 1 plus x squared over 1 plus x squared minus the derivative with respect to x of 1 minus x squared over 1 minus x squared. Right? So this is now equal to the derivative of x squared is equal to 2x over 1 plus x squared minus the derivative of 1 minus x squared is negative 2x all over 1 minus x squared. Now, combining these two terms, combining these two fractions here, this is now equal to the LCD would be 1 plus x squared multiplied by 1 minus x squared. So the LCD divided by 1 plus x squared is 1 minus x squared multiplied by this, so that will give us 2x, 1 minus x squared. Minus, right, so minus negative 2x multiplied by the LCD divided by 1 minus x squared, so that would be 1 plus x squared. So simplifying the numerator, we have 2x minus 2x cubed plus, alright, so this would now be negative times negative 2x times 1, so that would be 2x. Negative times negative 2x times positive x cubed, x squared, so that will give us positive 2x cubed all over 1 plus x squared, 1 minus x squared. right? So negative 2x cubed plus 2x cubed, so this will cancel out, and 2x plus 2x, so that will give us 4x. So y prime is now equal to 4x all over 1 plus x squared 1 minus x squared. So this would now be our final answer. And for our last example, we have y equals the natural logarithm of x plus 1 raised to 3 multiplied by x minus 1 quantity raised to 2 all over x minus 2 quantity raised to the second power. Solve for y prime. Right? So again, if we're going to inspect the given logarithmic function here, this whole function is u. Alright? And if you're going to think of it, we have a product, we have a power, and we have a quotient. Now, this is the importance of knowing the properties of logarithm, because in here, alright, so if we're going to transform this one using the properties of logarithm, again, ln of a over b is equal to the natural logarithm of a minus ln of b. So if we're going to apply that um, property, so y would now be equal to the natural logarithm of x plus 1 raised to 3 multiplied by x minus 1 raised to 2 minus the natural logarithm of x minus 2 raised to 2. Now, another property of natural logarithm is the logarithm of a multiplied by b, that's equal to the natural logarithm of a plus the natural logarithm of b. So applying this property in this term, then y can be written as ln of x plus 1 raised to 3 plus ln of x minus 1 raised to 2 minus ln of x minus 2 raised to 2. Right? And finally, another property of natural logarithm is the natural logarithm of a raised to k, which can be written as k ln of a. Alright, so applying this property in all of the terms here, then we can write y be equal to 3 ln of x plus 1 plus 2 ln of x minus 1 minus 2 ln of x minus 2. Now, we can easily solve for y prime in this expression, or in this form of the expression, rather than solving for y prime in this form of the expression. Now, this, or the value of this expression, is also the same as the value of this expression because we made use of several properties in here. Alright, so solving for y prime, this is now equal to 3 multiplied by the derivative of ln of x plus 1, so that's equal to 1 over x plus 1. Alright, so the derivative of x plus 1 is 1 over u, which is x plus 1, plus 2 multiplied by the derivative of ln of x minus 1, so that's equal to 1 over x minus 1. Alright, so the derivative of x minus 1 is 1 over x minus 1 minus 2 derivative of ln of x minus 2, so that will give us 1 over x minus 2. Right? So this is now equal to 3 over x plus 1 plus 2 over x minus 1 minus 2 over x minus 2. Right? So if we're going to continue with our solution here, we're just going to combine these three fractions. And combining it, we have LCD, which is x plus 1, x minus 1, x minus 2. So for this term, we have 3 multiplied by x minus 1, x minus 2. For this term, we have 2 multiplied by x plus 1, x minus 2. And for the last term, we have minus 2 multiplied by x plus 1, x minus 1. right? So we're just going to expand the numerator and we're just going to collect similar terms. So this is now equal to 3 multiplied by x squared minus 3x plus 2 plus 2 multiplied by x squared minus x minus 2 minus 2 multiplied by x squared minus 1 all over the denominator, which is x plus 1, x minus 1, x minus 2. So this is now equal to 3x squared plus 2x squared, so that will give us 5x squared minus 2x squared, so that will give us 3x squared. 3 times negative 3x, so that will give us negative 9x, right? So that's negative 9x. 2 times negative x, so that will give us negative 2x. And in here, we do not have our variable of x here, so negative 9x minus 2x, that give us minus 11x. And for the constant, we have 3 times positive 2, so that's positive 6. And then we have 2 times negative 2, so that is negative 4. And we have negative 2 times negative 1, so that will give us positive 2. So 6 minus 4, that is equal to positive 2 plus 2, so the constant would be positive 4. All over the denominator, which is x plus 1, x minus 1, and x minus 2. Alright, so this is now y prime written in simplest factored form. And that's how you solve problems involving derivatives of natural logarithmic functions.